Imagine you are hungry. Not I skipped lunch hungry, profoundly, architecturally hungry. The kind where your body has been running on empty for 2 days and your brain is doing that thing where it stops generating rational caution and starts generating desperate solutions. You are somewhere in the ancient world. Pick your era, pick your continent, and in front of you is something: a plant, a mushroom, an animal, a seed pod, something colorful and present and theoretically edible. You have no field guide, no internet, no poison control hotline, no grandparent nearby who tried this particular thing and survived to warn you. You have hunger and the object and a decision. You eat it. Sometimes you were fine. Sometimes you discovered something magnificent: a calorie dense root, a sweet fruit, a protein rich grub that became a staple. And sometimes you died. Badly. Quickly, or slowly, or in ways that your community watched and remembered and passed down as warning, which is how human beings built the accumulated food knowledge that became cuisine, agriculture, and eventually the concept of do not eat the red ones. The history of human food is inseparable from the history of human poisoning. Every safe food that exists today was made safe by a chain of ancestors who tried it when it wasn't safe yet, or who processed it incorrectly, or who ate too much, or who ate the wrong part, or who prepared it in the wrong season. The knowledge we take for granted: cook this, avoid that, soak before eating, never eat the leaves, only the root. That knowledge has a body count behind it that we never think about because we're too busy enjoying the results. So here is the actual story. The deadliest things ancient humans ate, the ones that killed people systematically across centuries, and the fascinating, horrifying, occasionally darkly funny ways those deaths shaped the food culture we inherited. Start with acorns, because they are a perfect entry point into the fundamental paradox of ancient food. Something that is simultaneously abundant, calorie dense, widely distributed across entire continents, and also completely toxic in its natural form. Acorns come from oak trees, which grow across enormous swaths of the northern hemisphere: Europe, Asia, North America. For ancient peoples in these regions, oak trees were impossible to ignore. They produced massive quantities of large, substantial nuts on a seasonal basis. They were everywhere. They were hard-shelled, which suggested durability. They were starchy, which suggested calories. Every sensory signal an acorn sends says, "Eat this." Raw acorns contain tannins, specifically tannic acid, at concentrations that cause severe gastrointestinal distress, kidney damage with repeated consumption, and in sufficient quantities, death. Tannins bind proteins, disrupt gut lining, inhibit nutrient absorption, and cause the kind of sustained digestive misery that leaves a person incapacitated. Ancient humans figured this out the hard way, over and over, in different regions independently, because acorns were just too abundant and too visually promising to leave alone. The solution, leaching, is one of the most remarkable pieces of food processing knowledge humans ever developed. By repeatedly soaking crushed acorns in water, either cold water over extended periods or hot water more quickly, the tannins dissolve out and the remaining starch is nutritious and safe. The problem is that this process is not intuitive. Nothing about looking at an acorn tells you to soak it in water for several days. Someone had to notice, probably over multiple painful trials, that acorns left near water sources tasted different, or that acorns processed with water were better tolerated. The development of intentional leaching represented a genuine cognitive and technological achievement, and the deaths that preceded it were the price of that knowledge. Indigenous peoples across North America used acorn meal as a dietary staple for thousands of years, with sophisticated leaching protocols that varied by region based on the tannin content of local oak species. What looks like a simple traditional food carries the entire weight of that discovery process behind it. Now move to something more dramatic. Bitter almonds, sweet almonds, the kind in your pantry, are safe, delicious even. But bitter almonds, the wild form, contain amygdalin, a compound that your digestive enzymes convert into hydrogen cyanide, actual cyanide. The same compound, the same mechanism used in chemical weapons and execution chambers. In sufficient quantities, bitter almonds kill through cellular asphyxiation. Your cells lose the ability to use oxygen and essentially suffocate despite the presence of normal oxygen levels in the blood. It's a particularly cruel mechanism. Ancient humans encountered bitter almonds constantly because wild almond trees are not labeled. They look like the trees that produce safe almonds. The nuts look similar, The smell is similar, though distinctively more pungent in the bitter variety. Early almond consumption was likely a continuous low-level poisoning problem. Not everyone eating a few bitter almonds dies, because the lethal dose varies with body weight and the specific amygdalin concentration in a given nut. But chronic exposure and accidental high-dose ingestion killed people regularly. The domestication of sweet almonds, the selective cultivation of low amygdalin varieties over thousands of years eliminated this problem for most people. But the wild bitter almond is still out there, still growing across Central Asia and the Mediterranean. The selective pressure that made humans preferentially cultivate sweet varieties was, at least in part, survival pressure. The people who knew which trees were safe were more likely to survive. The knowledge became agricultural practice. Cassava deserves its own lengthy discussion because it is one of the most complex food safety stories in human history, and one that continues to cause deaths in the modern world, let alone the ancient one. Cassava, also called manioc or yucca, is a root crop that was domesticated in South America roughly 10,000 years ago and has since spread to become a dietary staple for hundreds of millions of people across Africa, Asia, and Latin America. It is drought-tolerant, grows in poor soils, produces enormous caloric yields, and stores well. From an agricultural standpoint, it's one of the most important crops ever developed. It also contains cyanogenic glycosides, the same general category of compound as bitter almonds, at concentrations that vary between varieties, but can be high enough to cause death from hydrogen cyanide poisoning if the root is eaten improperly prepared. There are two basic types of cassava: sweet cassava with low cyanide content, and bitter cassava with high cyanide content. Bitter cassava requires processing, grating, squeezing, heating, or fermentation to render it safe. The processing knowledge is extensive, sophisticated, and has been developed by human communities over millennia. Different cultures have different methods: fermentation, pressing with specialized tools, extended cooking, sun drying. All of them work through the same mechanism, driving off or breaking down these cyanogenic compounds. The ancient people who developed these methods were working without any knowledge of cyanide chemistry. They observed effects. People who ate unprocessed bitter cassava got sick, sometimes died. People who processed it in particular ways were fine. They built processing protocols around observed outcomes, not understood mechanisms. The result was a body of food safety knowledge that was passed down through generations and was accurate and effective despite being entirely empirical. The deaths that generated this knowledge were real. Acute cassava cyanide poisoning produces symptoms that escalate from nausea and dizziness to convulsions and respiratory failure within hours. In communities that lost traditional processing knowledge, through displacement, cultural disruption, famine forcing rapid consumption of improperly prepared food, mass poisoning events occurred. This wasn't only an ancient problem, it has happened in living memory in various parts of Africa during famines when people consumed improperly processed bitter cassava out of desperation. The ancient lesson, the crop that saved civilizations from starvation, required knowledge to use safely, and when that knowledge broke down, the crop became the cause of death rather than its prevention. Elderberries. Another case where the gap between safe and deadly is paper-thin and depends entirely on what you do with the plant. Elder, Sambucus species, grows across Europe, North America, and parts of Asia. Every part of the plant except the ripe cooked berry contains toxic alkaloids and cyanogenic glycosides. The leaves, the bark, the roots, the unripe berries, and the seeds inside the ripe berries, all dangerous. Raw, unripe elderberries cause severe nausea and vomiting. Consumption of leaves or bark causes more serious systemic poisoning. Ancient people discovered elderberries in a landscape full of wild berries, many of which were safe to eat raw. The visual resemblance to safer berry species, combined with the elder's enormous productivity and the genuine nutritive value of properly prepared ripe berries, made it irresistible as a food source. But the safety window is narrow, fully ripe, cooked, with seeds removed or juice strained. Outside that window, elder is actively harmful. The traditional uses of elderberries across European cultures, elderberry wine, elderberry cordial, cooked elderberry preparations, all reflect the accumulated knowledge that cooking is essential. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Recipes for raw elderberry preparations essentially don't exist in traditional cuisine because raw preparation doesn't survive as tradition. The people who tried it repeatedly didn't pass down that particular habit. What you eat raw, what you cook, what you ferment, what you process, these categories in traditional food culture exist because of the deaths that defined their boundaries. Blood and organ meats from certain animals occupy a different category of danger, not because of inherent chemical toxicity, but because of parasitic and bacterial contamination that ancient humans had no framework for understanding. Trichinella, a parasitic roundworm found in the muscle tissue of pigs, bears, and various wild game animals, causes trichinosis, a disease producing fever, muscle pain, facial swelling, and in severe cases, cardiac and neurological complications leading to death. The worm's larvae encyst in muscle tissue and are only destroyed by thorough cooking. Raw or undercooked pork and wild game were a systematic vector for this parasite in ancient populations. Ancient peoples across Europe and the Middle East consumed a great deal of raw and lightly cooked pork and game. The connection between this food and subsequent illness was not understood mechanically. Germ theory didn't exist. The concept of microscopic parasites was beyond the observational technology available. But the association between certain animals and illness was noticed and encoded into cultural practice. The Hebrew prohibition on pork, often discussed in purely religious terms, may partially reflect accumulated empirical observation that pork caused illness more consistently than other meats in the ancient Near Eastern climate, where warm temperatures accelerated spoilage and created favorable conditions for trichinella. Similar patterns appear in other cultures. Avoidances of certain raw animal products that, when examined through a modern microbiological lens, map onto real contamination risks. The religious framing preserved the behavioral outcome without requiring knowledge of the mechanism, which is, honestly, a clever solution. Liver deserves specific mention here. Raw liver, particularly from large animals, was consumed across many ancient cultures as a concentrated source of nutrients and was treated in some contexts as almost medicinal in its potency. It is extremely dense in vitamins and protein. It is also extremely dense in vitamin A, to the degree that consuming large quantities of certain livers, polar bear, seal, and other Arctic animals most dramatically, causes hypervitaminosis a syndrome characterized by severe headache, dizziness, skin peeling, bone pain, and in extreme cases, death. Arctic peoples who ate marine mammals learned through experience which organs were safe to consume in what quantities. The liver taboos present in various Inuit and other Arctic cultures, warnings against eating large quantities of certain liver types, particularly of carnivorous animals, reflect this accumulated toxicological knowledge. The danger was real. Large predator livers concentrate vitamin A at levels that are functionally toxic to humans, and people died discovering this. Wild mushrooms represent perhaps the single most consistent killing food across all of human history, on every continent where fungi grow, across every era, and they represent it in a specific way that makes them particularly interesting as a case study in ancient human risk assessment. The problem with wild mushrooms is not that they're complicated to identify. The problem is that the most dangerous ones, the species responsible for the overwhelming majority of mushroom-related deaths globally, look ordinary. The death cap, Amanita phalloides, looks like various safe mushroom species. It has no dramatic coloration, no warning smell, no immediate taste indication that anything is wrong. It tastes, by various historical accounts, reasonably pleasant. And it contains amatoxins that take 12 to 24 hours to produce any symptoms at all. That delay is the mechanism of death. By the time a person who has eaten deathcap feels anything is wrong, the toxin has been working on their liver for half a day. The amatoxins inhibit RNA polymerase II, which is the enzyme responsible for cellular protein synthesis. Essentially, they stop cells from producing the proteins they need to function. Liver failure follows, typically over several days, during which the person may appear to be recovering from initial symptoms before deteriorating catastrophically. Ancient humans foraging mushrooms had no way to anticipate this. The death cap gives nothing away at consumption. The time delay between eating and symptoms severed the cognitive connection between cause and effect. A forager who ate deathcap in the morning might not feel symptoms until the following morning, and by that time had presumably eaten other things, moved locations, and had no clear reason to identify the mushroom as the source. Establishing the connection between a specific mushroom and delayed onset liver failure requires the kind of systematic observation that is very hard to conduct in a subsistence lifestyle. Death caps and their relatives, the destroying angel, Amanita bisporigera, being equally lethal, have killed people throughout human history in every region where they grow. They continue to kill people today, most commonly in cases where people from cultures without local mushroom knowledge move to regions with Amanita species and fail to recognize the danger. The deaths are not the result of recklessness. They are the result of a poison that has evolved a remarkably effective concealment strategy. Ergot is one of the most important and most disturbing entries on this list because it killed people not through a single acute poisoning event, but through chronic exposure that caused symptoms that ancient peoples had no framework to interpret as food poisoning at all. Ergot is a fungal parasite, Claviceps purpurea, that infects rye and other cereal grasses. An infected rye plant develops dark, elongated structures called sclerotia, the ergot bodies, that replace some grain kernels. Ergot contains ergot alkaloids, compounds that cause two distinct syndromes depending on which alkaloids predominate. The first syndrome is gangrenous ergotism, also called St. Anthony's fire in medieval Europe, where the vasoconstricting effects of ergot alkaloids cut off circulation to the extremities. Fingers, toes, hands, and feet essentially die on the living person. They blacken, develop a burning sensation, and eventually fall off. Whole limbs were lost. The pain was described as intense burning, which is where the fire in the medieval name originated. The second syndrome is convulsive ergotism, neurological symptoms including seizures, spasms, hallucinations, and altered states of consciousness. Ergot alkaloids are structurally related to lysergic acid, the base compound from which LSD was later derived. Mass ergot poisoning events in communities eating contaminated rye bread produced what looked, to contemporary observers, like demonic possession, supernatural visitation, or divine punishment. The dancing plagues of medieval Europe, where groups of people danced uncontrollably for days, have been speculatively linked to ergot poisoning. The Salem witch trials have been analyzed through the lens of ergot, with some historians suggesting that the afflictions described by accusers during that period showed features consistent with convulsive ergotism. Ancient and medieval grain consumers had no way to identify ergot as a contaminant. The dark sclerosia were present in the grain supply, were ground into flour, and ended up in bread without any obvious sign that something was wrong. Wet years that favored fungal growth in grain fields were followed by outbreak years of St. Anthony's fire. The connection to grain was not understood. The connection to wet weather creating contaminated harvests was not understood. People were experiencing physiological catastrophe with no comprehensible cause, which is in some ways worse than understanding what's happening to you. The elimination of ergotism as a major public health problem required the development of grain inspection and eventually modern agricultural practices that reduced ergot contamination. It was not resolved through understanding the mechanism. It was resolved through practices that happened to address the problem without anyone initially knowing why they worked. Fava beans belong on this list for a reason that illuminates something remarkable about human genetic variation and its interaction with food safety. They are safe for most people and potentially lethal for others, depending on a genetic trait that the ancient world had no way to identify. Favism, the condition in which consumption of fava beans triggers hemolytic anemia in susceptible individuals, results from a genetic deficiency of the enzyme glucose 6-phosphate dehydrogenase, known as G6PD deficiency. People with this deficiency cannot process certain oxidative compounds in fava beans, and the result is rapid destruction of red blood cells, causing severe anemia, kidney failure, and potentially death. G6PD deficiency is not rare. It affects hundreds of millions of people globally, with highest prevalence in populations from the Mediterranean, Africa, and South Asia. The geographic overlap with fava bean cultivation is not a coincidence. The deficiency provides some protection against malaria, which is why it persisted at high frequency in malaria endemic regions despite the food safety problem it created. In ancient Mediterranean cultures where fava beans were a dietary staple and G6PD deficiency was common, the result was a category of mysterious deaths in which some community members could eat a food with no obvious consequence, while others, eating the same thing at the same table, became gravely ill. The Pythagorean prohibition on fava beans is the most famous ancient reference to this problem. The exact reasoning behind Pythagoras' famous instruction never to eat beans has been debated for millennia, but favism has been seriously proposed as the practical origin. Whatever the reason, the cultural taboo preserved a food safety behavior without the underlying mechanism being understood. Raw red kidney beans represent a similar category of hidden danger, one that many people in the modern world have rediscovered through the rise of slow cookers. Raw kidney beans contain phytohemagglutinin, a lectin that causes severe gastrointestinal toxicity, violent nausea, vomiting, and diarrhea beginning within hours of consumption. The compound is destroyed by boiling for at least 10 minutes, but it is actually concentrated by low-temperature cooking, meaning kidney beans cooked in a slow cooker that never reaches boiling temperature can cause more severe poisoning than eating the same beans raw. Ancient peoples who developed kidney beans as a food crop did so through the same empirical process as every other dangerous food, observing who got sick, identifying patterns, developing processing protocols that worked. Boiling legumes is standard traditional preparation globally, and that standard exists in large part because the people who didn't boil them adequately suffered for it. The beans are fine. The laziness, or in ancient context, the fuel scarcity, is what kills you. Sassafras is a case study in a food ingredient that was popular, widespread, beloved, and then discovered to be carcinogenic, with the ancient use predating that discovery by millennia, and the deaths it caused accumulating slowly enough to be invisible in any individual lifetime. Saffrole, the compound that gives sassafras root bark its distinctive flavor and fragrance, is a hepatic carcinogen. It causes liver cancer with chronic exposure. Indigenous North Americans used sassafras extensively as a food and medicine. Colonial Americans made root beer from sassafras root bark. Saffrole-containing products were widely consumed across centuries. The deaths that resulted were not dramatic. No one collapsed after a cup of sassafras tea. What saffrole does is probabilistic and cumulative. It increases cancer risk over years and decades, shifting the statistical distribution of liver cancer upward in populations with chronic exposure. The ancient and early modern people consuming sassafras had no way to observe this because the causal chain between daily tea and liver cancer 20 years later is invisible without epidemiological tools that didn't exist. The removal of saffrole from commercial food products in the United States happened in 1960 after animal studies demonstrated the carcinogenicity. But for everyone who drank sassafras tea for generations before that, the danger was real, just undetectable. Pulling all of this together, a pattern emerges that is worth sitting with. Every deadly food on this list, acorns, bitter almonds, cassava, elderberries, contaminated meat, death cap mushrooms, ergot, fava beans, kidney beans, sassafras, was consumed by ancient humans not out of stupidity, but out of necessity and rational information seeking within the constraints of the knowledge available to them. Nobody chose to poison themselves. Everyone was doing the same thing, evaluating a potential food source against hunger, using the observational tools they had, trying to find something that would keep them alive. The knowledge that emerged from those deaths — soak acorns, cook elderberries, process cassava, avoid ergot-contaminated grain, boil your legumes — is encoded in food culture so deeply that most people follow these rules without knowing their rules at all. We cook, we process. We have cuisines with specific preparation methods and ingredient combinations that seem arbitrary until you understand what they were designed to prevent. The ancient food supply was not a pastoral idyll of natural abundance. It was a minefield of chemical defenses, microbial hazards, parasitic risks, and hidden physiological dangers that killed people systematically for as long as humans have existed. The safeness of the modern food supply, such as it is, was purchased with the lives of people who ate the wrong thing and didn't survive to pass down what not to do. Every meal you eat that doesn't kill you is, in a very real sense, the product of their deaths. The least we can do is know their story.